Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay. Okay, so we will consider this convex optimization problem of minimizing convex function fx such that x is subject to this convex set. That is, x should belong to, is constrained to this set of values. Okay, and one way to ensure that this set is convex is that you assume each fix is convex and hjx is a affine constraint, a linear constraint. Okay. For example, so we will have, let's say, minimize maybe x transpose ax such that x transpose bx is less than equal to 0 and ax is equal to, or cx is equal to d. Okay, so, and we'll, here A is a positive definite matrix, B is a positive definite matrix. So if you recall, positive definite matrices are matrices whose eigenvalues are all positive. Okay, so if that happens, then this is a convex function, this is a convex function, and that's why this will be a convex set, and this is also, this is a linear function, and that's why this set will be a convex set, and this is a convex function. So we are minimizing convex function subject to a convex set. Okay, and then last time we saw that, okay, one approach to solve this problem is that, okay, you try to find out x which will minimize this. So what you can try to do is some simple methods, like you say that at each step xt or at each step t I have some iterate xt. Okay, so let's say this is my convex set C to which I want my xt to belong to. So let's say initially xt is somewhere here. Now what I do is I take a step in the direction of gradient of this function. I want to minimize this function, I want to take a step in the direction of this gradient, and what can happen is that now my next point xt plus 1 can go out of the convex set. So a simple way to handle this problem is that, okay, let's project back xt plus 1 to this set. Okay, just take a projection onto this set and just keep on repeating this. So now my xt plus 1 will be this. Again, I will take a step in the direction of gradient, maybe it will in this direction. I will take a projection, this will be my xt plus 2, and I'll just keep on doing this. Okay. So this is called the method of projected gradient descent. Okay. So if you have a simple convex optimization problem where this projection is easy, or it is reasonably easy to do for you, then it's a very easy method to implement. Okay. And then remember, like for unconstrained optimization problems, we talked about Newton-Raphson type of method, where rather than just updating my xt plus 1 as xt minus some eta times gradient of f at xt, so this is just gradient descent update. You do you use Hessian information as well, that is xt plus 1 is equal to xt minus h inverse gradient of f at xt, right? So you can try to do this type of thing in the case of constraint optimization as well. That is, now this point will be given by this, and then you can make a projection. But you cannot do it this easily, as in what happens is when you want to use this Newton type of methods, people actually, like, many times just do this because for several problems it converges to the optimal solution. But this is theoretically incorrect, as in you can have counter examples where it will not converge to the optimal solution. So you need to do little bit of modifications here, and those methods are called trust region or active set methods, where you have to determine what all variables are active, and according to them you do this update. So I won't go into those methods today, but I mean, just for as a recipe, if you want, you can do it, but it need not converge to the optimal solutions. You should be aware of this fact always, and if you want to do the correct thing, then you should look into the literature of active set methods. Okay, so this was just a sort of side view. So in last class we were talking about, whenever we have this constraint optimization problem, maybe it is good if we look at the dual of this problem, and we wanted to understand what does solving dual problem means, what are the properties of dual problems, and when all it can be useful, right? So in this class we'll mostly talk about that. So let's get back to our constraint optimization problem, which is given by this, and then one recipe that we discussed for forming dual was first form the Lagrangian, okay, which is fx plus summation lambda I fix plus summation nu j hjx, right? And then you form this dual function, which is just a function of lambda and nu, by minimizing over all x that belongs to the domain of f, okay, and then your dual optimization problem will be maximize g lambda nu such that lambda is greater than equal to 0, that is lambda I greater than equal to 0 for all I. Okay, this is what we discussed last time. And then we said that, okay, no matter what fx, fix, hjx are, whether they are convex or not convex, g lambda nu will always be, number one, concave, number two, it will always lower bound my function fx. Okay, so let's look into those two properties a little bit more closely. So first we said that g lambda nu is concave irrespective of f, fi and gj, right? So can anyone tell me why is it so? Why is it concave? Why g lambda nu is a concave function? So a concave function is essentially negative of a convex function. And if you look at it, this is, so if I take a negative of g lambda nu, this will be what? Maximization of this negative thing, negative of this, right? So it is a pointwise maximum of a function, right? And that function is linear in lambda and nu, my parameter vector. So it is convex, okay? So it is pointwise maximum of a convex function. So it should also be, so minus of g lambda nu should be convex, and that's why g lambda nu should be concave. So let's just work that out more formally. So let's look at alpha lambda plus 1 minus alpha lambda prime and alpha nu plus 1 minus alpha nu prime, right? This is equal to, so if I want to prove that g lambda nu is concave, then I want to show that this quantity is greater than equal to alpha g lambda comma nu plus 1 minus alpha g lambda prime nu prime, right? That is for any 2 points lambda comma nu and lambda prime comma nu prime, alpha of this plus 1 minus alpha of this is less than equal to this. Pictorially what it means is, this is my point lambda comma nu, this is some other point lambda prime comma nu prime, and what I want to say is that on this line my function value is always larger than the function value that I obtain by interpolating my function values at these 2 points, right? So this is the interpolation values, and I want to say that this is always smaller than the actual function value at all these intermediate points, right? So now this is what we want to prove. So now we know that this is equal to minimize over all x belongs to D, f of x alpha plus, I'm just writing out this thing, so y alpha. So this is equal to fx plus summation lambda I fix times alpha plus summation mu j or nu j hgx times alpha plus summation lambda I prime fix 1 minus alpha plus summation mu j hgx 1 minus alpha, right? This just follows from definition of this guy, and then we say that okay, minimizer of this whole thing will be larger than minimizer of when, like, if I break this whole thing into 2 components. So if I minimize each of the individual component, that value will be smaller than this overall minimizer. So I break fx also in 2 components, alpha fx plus 1 minus alpha fx, right? And I take this component separately and then this component separately, right? So this component, as you can see, this is just alpha times g of lambda comma nu, and then minimize x over d. This component is just 1 minus alpha g of lambda prime nu prime, right? So we have what we wanted, that is this linear interpolation of these function values is less than equal to the function value itself in the intermediate points. Okay. So now this property is clear, which is a very critical property, that, and here we didn't use any convexity of f at all, right? We just use that g is a minimizing function and it is linear in lambda and nu. That's all we needed, and that was enough. Okay. And then second property that we use, or that we saw, is g lambda nu maximum over all lambda comma nu, lambda greater than equal to 0 and all nu, is less than equal to minimizer of this, where such that fix is less than equal to 0 and hgx is. So this is my primal problem, right? And this is my dual problem. So this essentially says that my minimum value of primal problem is always greater than equal to the maximum value of dual problem. Okay. And again, how does it follow? And this is called weak duality condition. Okay. So again, it follows fairly easily. So if you look at G lambda nu, that is equal to minimizer of x belongs to D fx the summation lambda I fix plus mu j hjx. And now I know that if x is a primal feasible solution, that is, it satisfies these two constraints, then this will be 0 because hjx will be 0, right? And this quantity will be less than equal to 0 because lambda is positive. It's a dual feasible variable, so lambda is positive and fix is less than equal to 0. Okay. So this whole quantity will always be less than equal to fx, where x is primal feasible, that is, x belongs to this convex set C. Okay. So it's clear why dual is sort of lower bounding my primal. So remember last time also we drew this picture that suppose this is my primal problem and like primal objective function, and this is my dual objective function. Then dual number 1 is always below primal, and this gap between primal optimal and the dual optimal is called duality gap. Okay. So that is one. Second condition is that and another thing is that my dual is always concave. So dual is always sort of easier to solve. It is always a concave function subject to bunch of positivity constraints. So for example, this projected gradient descent method that I told you, you'll find it fairly easy to do or apply it for dual problem if you can write down this G lambda nu nicely. So sometimes writing dual problem itself can be very challenging. It can be very tricky. But if you can do that, then this optimization problem is reasonably easy to solve because you can use standard gradient descent method and actually you can do bunch of other things. Okay. Like not just gradient descent but projected gradient descent. Projection onto this set is very easy. This is positivity constraint set. So projection onto this set is, so suppose if I want to project a vector x onto this so suppose I have any vector lambda and I want to find out another vector lambda prime such that 2 norm square is minimized, right? And lambda prime I is greater than equal to 0. That is, this is lambda prime is projection of lambda. So this is fairly easy to do. I mean, it's fairly easy to see that your lambda I prime will be equal to maximum of 0 comma lambda I. So if your lambda is already positive, you don't do anything with it. And if your lambda I is negative, then you just set it to be 0. You just clip it. It's just a clipping operation. So doing projected gradient descent on this dual problem is very easy or relatively easy. Okay. And that is one of the primary reason why people like to use this like dual formulation. But then there is no guarantee that whatever the optimal solution you obtained, it can be far away from the true optimal solution. Okay. So when can we guarantee that there will be like the optimum of my dual problem will be truly or will correspond to the true optima of the primal problem? You can guarantee that as long as your function fx, fix are convex, hjx is a linear constraint, or linear objective function, sorry, linear function or affine function, and you need to satisfy some other condition as well. That is not just enough. Just convexity will not suffice. Okay. So other than convexity, you need some other condition, some fairly mild condition, but some other condition. And one of the most popular of such conditions is called Slater's condition. So I'll tell you that, but let me just draw the picture. So what will happen is that if you have, let's say, Slater conditions are satisfied and each of your function is convex, and basically if your function is convex, your set is convex, then this will be the picture. That is, at the minimum point of fx, g lambda nu will touch it. Okay. So you get to this point either by maximizing dual or by minimizing primal. It's the same. The rates might be different and there might be some other issues, but the solution will be same, or set of solutions will be same. Okay. And in fact, you can do some things much more fancy, where you work for a little bit in primal, you work for a little bit in dual, and keep on alternating. So these are called primal dual methods. So they exploit both structure of primal problem as well as dual problem. So naturally we won't go into all that, but let me now mention the Slater conditions under which you have this optimality gap to be 0, or this duality gap to be 0. Okay. This. Okay. So conditions for strong duality. So f and fi should be convex. Hj should all be affine functions. Okay. And there exists a x that belongs to relative interior of D. So relative interior of D is essentially, so D is your domain of function f, right? It is a set over which function f is defined. So let's say this is the set. So what you want is that somewhere in interior of this set there exists a point x. Okay, let's say this point x, which belongs to interior of this set D, such that fix is strictly less than 0 and hjx is equal to 0. That is, these conditions are satisfied with strict inequality. Okay. So you don't only want a feasible point in your domain, you want that feasible point to satisfy this set of inequalities strictly. Okay. If that happens, then you can say that my duality gap will be 0. Okay. So these are called Slater's condition. So many times people, whenever they say that, okay, I have to minimize the convex function subject to convex set, and that's why I can solve it and solve it easily. It is polynomial time solvable. It is actually incorrect. That statement technically is incorrect. You require some other conditions along with those convexity to say that, okay, my duality gap is 0 and I will be able to solve the problem efficiently. In fact, there are NP hard problems, or I don't know, hard, yeah, definitely hard, NP hard problems, which can be written as these convex programming problem. In fact, it can be written as a linear programming problem. For example, maximum independent set. It can be written as a linear programming problem. Still, you cannot solve it. Still, the duality gap is non-zero. And the reason is that they do not satisfy the Slater conditions or some of these nicer conditions. Okay. So that is one form of Slater condition. There is a weaker class of Slater conditions, which says that okay, if so, sort of weaker conditions. So your weaker conditions are that if let's say f1, f2 till fk are affine, okay, so they are constraints of the type aix is less than equal to bi, okay. If they are affine constraints, then they can be satisfied with inequality, okay. That is fix can be less than equal to 0 for I less than equal to k greater than equal to 1, okay. And your fix should be strictly less than 0 for all the other constraints. So let's say if I have m constraints which are not affine, for them I should satisfy the constraint with inequality, okay, and my hjx should be equal to 0. So if this, then there exists x belongs to relative interior of my domain such that this is satisfied, okay. So these are sort of weaker set of conditions, weaker set of Slater conditions. So either if this happens or this happens, then we say that the duality gap is 0 and my strong duality holds. So weak duality was that g of lambda star nu star is less than equal to f of x star, where so I'm putting star as to denote the optimal solutions which are feasible as well. So that is lambda star is positive and then x star belongs to my this set C. They are primal feasible as well as dual feasible, okay. So this is just weak duality. Strong duality says that actually they are equal. And the strong duality hold as long as my Slater conditions hold and my functions are convex or Hj is affine, okay. Is this clear? This concept of weak duality, strong duality. So if my strong duality holds, then it doesn't matter if I solve primal or dual, I will get to the optimal solution, okay. So let's consider one example. So example is our standard linear programming. So suppose I want to minimize C transpose X such that Ex is less than equal to B and X is greater than equal to 0. Okay. Okay. So even before beginning, let me first derive the dual and then we'll talk about strong duality. Okay. So this happens. Now we want to find out the dual of this linear programming problem, okay. And this actually duality is extremely popular tool for solving linear programming problems, because for several combinatorial problems like max flow etc., they can be written as a linear programming problem, and there duality plays an important role in devising very fast algorithms. So it's extensively studied there. So I'll assign assign a set of variables lambdas here, and this I can write as minus x less than equal to 0, and I'll assign some variables new for this. Okay. This is equal to C transpose x plus, so this also can be written as ax minus b is less than equal to 0, minus nu transpose x. This is my Lagrangian, and I'll require my lambdas to be positive and nu's to be positive because these are inequality constraints. Okay. And this is equal to C transpose or C plus A transpose lambda minus nu transpose x minus B transpose or lambda transpose B. Okay. I've just collected my terms for x. Okay. Is clear? And now G lambda nu, which is given by minimizer of x of Lagrangian. Look at it. So this is the constant. So I can just bring this out, minus B transpose lambda plus minimizer of x C plus A transpose lambda minus nu transpose x. Right? So this is a linear function and this is just constant with respect to x, right? So if you consider any linear function, let's say this is my fx, this is x, and I have a linear function, right? So what is the minimum value of a linear function? So let's say this function is c times x. So unconstrained, if it is unconstrained, then it is minus infinity. I can take it to as low as I want. It is unbound, it is bounded only when c is equal to 0, that is fx is equal to 0. In only that case it is bounded, otherwise it is unbounded, right? So what does it mean here? That I can pull this value to minus infinity if C plus A transpose lambda minus nu is not equal to 0, right? That's why I can write G lambda nu to be minus B transpose lambda if C plus A transpose lambda minus nu is equal to 0. Otherwise it is minus infinity. Okay, right? Now recall that my dual problem was maximize G lambda nu such that lambda is positive, nu is positive, right? This will be my dual problem. So naturally I will not consider these cases where C plus A transpose lambda minus nu is not equal to 0, because then my G lambda nu is minus infinity. So I don't even need to consider those cases, right? I can write, so basically this dual problem can now be equivalently written as maximize minus B transpose lambda such that C plus A transpose lambda minus nu is equal to 0. Lambda is positive, nu is positive, right? And so this will say that this is equal to nu, and since nu is positive, so, and this is the only place where nu appears, so I can easily eliminate nu and I can say that C plus A transpose lambda is greater than equal to 0, right? Because that's where nu appears, nu doesn't appear anywhere else, right? So earlier I was saying that C plus A transpose lambda is equal to a positive quantity. Now also I am saying exactly the same thing, that C plus A transpose lambda is a positive quantity. Okay, and I should So I can eliminate lambda mu. So now my optimization problem is maximize minus B transpose lambda such that A transpose lambda is greater than or equal to minus C and lambda is positive. Okay. So one interesting thing is that my primal was a linear program, my dual is also a linear program. Okay. And all it does is basically it takes this C in constraints and it takes these B in the objective function. So there is a duality between objective function and the constraints. And there are actually some more geometric interpretation of this thing, but today we will not go into that. But the bottom line is that, okay, this holds. Right? So now I want to understand, if I have this linear programming problem, when can I say that, okay, my strong duality holds? That is, if I solve my dual, I'll solve my primal as well. And the answer comes from this weaker Slater conditions. So note that here I don't have any non-affine constraints. All my constraints are affine. So the Slater conditions will essentially boil down to this one single condition, that there should be a primal feasible solution. That is, there should be a solution X such that Ax is less than or equal to B and X is positive. That's it. So as long as I have a primal feasibility, that will actually imply dual feasibility as well, and my strong duality will hold. Okay, as long as you can demonstrate that. Clear? So primal dual feasibility for LP implies strong duality. Okay, and then basically I can solve either the primal, dual, I can mix and match, do whatever I want. Okay. So let's take one more example, then we'll get to KKT conditions. Okay. So consider an optimization problem of this type. Minimize X transpose X such that Ax is equal to B. And in practice, this type of problems occur quite a bit. I mean, quadratic program subject to linear constraints or least square type of problems. So they all have similar flavor, and their dual problem also are very similar. So okay, so actually even before beginning, if you look at Slater conditions, here see all the constraints are affine. So Slater condition, well anyways these are equality constraints. So even if they were inequality constraints, as long as there was a feasible solution, Slater conditions will say that strong duality will hold. Compute the dual problem and there will not be any duality gap. Okay. So as long as if you have a affine set, then as long as you can demonstrate feasibility, that is there will be at least one feasible solution, primal feasible solution, one point X such that Ax is less than or equal to B and X belongs to relative interior of this set. So here my function fx is, it is defined everywhere. So I don't need to worry about the relative interior business at all. As long as I can demonstrate feasibility, I'm done. I can blindly use dual problem formulation. Okay. So this is nice. Now here today we'll just work with equality. Okay. And basically I'm using this equality to prove one point, basically to show usefulness of dual problems. So if you look at this problem as it is, I mean, it seems like you'll need to do quite a bit of work to solve it, right? Because you might want to do this projected gradient method or Newton method or whatever. But this set is a polytope. It's not a very nice set, and you'll need to keep on projecting onto this set, which can be hard, etc. But we'll see that when we go to dual, the solution becomes, I mean, fairly easy. It's in fact almost a sort of closed form solution. Okay. So let's understand its dual. So let's write its Lagrangian. So there are variables lambda attached here, and since it's a equality constraint, so lambda are free. I don't need to constrain lambda to be positive or anything. Lambda can take any value they want. So that is given by x transpose x plus lambda transpose ax minus b. This is because equal to ax minus b equal to 0, right? And then when I compute g of lambda, that is minimizer of the Lagrangian, right? So to minimize Lagrangian, and x is defined everywhere, so I don't need to constrain x to any set, right? So I can just take its derivative to minimize the Lagrangian, right? So I take its derivative, so derivative will give me twice x plus A transpose lambda is equal to 0. This will give me twice x, this will give me A transpose lambda. Third term is a constant, so it goes away. That is x is equal to minus 1 by 2 A transpose lambda. Okay. So I put back this condition or this value of x back in my Lagrangian. Okay. And what that will give me is 1 by 4 lambda transpose A transpose lambda. Okay, I'm just replacing x with this, minus lambda transpose A transpose lambda by 2 minus lambda transpose B. Okay, so this 1 by 4 will cancel with minus 1 by 2, so this will, I'll just get minus 1 by 4 lambda transpose A transpose lambda minus lambda transpose B. Okay, so one very quick thing to check whether you computed your, this will be my g of nu, right? If you computed your dual properly, you have to check that the dual function is concave or not, and it's very easy to see that it is, because A transpose is a positive definite matrix, so this function lambda transpose A transpose lambda is convex, and negative of it will be concave, right? So now your dual problem will be what? Why did I write nu here? This should be lambda. Okay, so my dual problem is maximize g lambda such that, well, I don't have any condition on lambda here, lambdas are free, so just I have to maximize this quantity. Okay, so this becomes now, so I have to just, so this is just a unconstrained optimization problem. So this is equal to minimizing 1 by 4 lambda transpose A lambda, A transpose lambda plus lambda transpose B. Okay, so it's a unconstrained optimization problem, and in fact you can obtain its closed form solution as well. You have to just write it as a least square problem. Okay, so while in primal problem was looking very complicated, when I went to dual the problem became significantly easy, and it gives nice insight about the geometry of the problem as well. Okay, and once you find, another question is, okay, so I solved dual, how do I get my primal solution? Because that's what I'm interested in. I don't care about these lambdas, right? I want my x, optimal x. So once you solve for lambda, you can obtain x by using this fact. Okay. So this is well and good. Now let's look at a very popular set of conditions called KKT condition or Karush-Tucker conditions, which are used to characterize primal and dual optimal solutions. Okay. And so these conditions are, so let me write it down. So these conditions are necessary conditions for any optimization problem, for optimality of any optimization problem. So whether you have convex functions, whether you have Slater condition, it doesn't matter. These are necessary conditions for any optimization problem. Okay. But they become sufficient also if strong duality holds. That is, if your functions are convex and have Slater condition, etc., then this actually characterizes your necessary as well as sufficient conditions. So these are very powerful conditions. Okay. Conditions are fairly easy. So there are three types of conditions. First is feasibility, primal and dual feasibility. So let me define notation. So I'll assume that my x star is primal optimal and lambda comma nu, lambda star nu star will be my dual optimal. Okay. So the conditions that x star and lambda star nu star should satisfy is first primal feasibility, primal and dual feasibility, which is sort of natural. Like I'm calling them to be solutions, so they should be feasible solutions. That is, my fi x star should be less than equal to 0 for all I. My hg x star should be equal to 0. And my lambda I star should be greater than equal to 0. So this I am writing assuming our general form. Minimize fx such that fix is less than equal to 0. X is equal to 0. Okay. So primal dual feasibility. Second is sort of stationarity condition, that is gradient of Lagrangian with respect to x at computed at x star, lambda star, nu star should be equal to 0. Okay, so this is sort of a stationarity condition. And third condition is very interesting. It's called complementary slackness condition. And what it says is my lambda I star fix star should be equal to 0 for all I. And well, it holds for the other thing as well, but that doesn't make much sense. Because by just the feasibility itself it holds. So this is more interesting. Is lambda star fix star is equal to 0. So that is either my dual variable will be non-zero. Okay. In that case, if my dual variable is non-zero, in that case my fix star has to be 0. That is, I have to lie on the boundary of my set. If my dual variable is active, it is non-zero, then I have to lie on the boundary of the set. Okay, and if I am in the interior, then my dual variable has to be 0. So dual variable will be non-zero only if I am at the boundary of that particular constraint. So if you give me a dual solution or optimal of my dual problem, I can look at all my Lagrangians and I can tell you that, okay, this constraint is satisfied with equality, this constraint is satisfied without equality, just by looking at them, because of this complementary slackness condition. And the reason it arises is also very simple. I mean, it comes about because of, it's a very powerful tool or inequality and equality, and I mean it is used, for example, like it is for several problems it is used to construct primal feasible solution or primal optimal solution from dual optimal or vice versa. It's very useful, but it arises in a very simple manner. So we know that strong duality holds. That's why I know that G of lambda star nu star is equal to f of x star, right? And I know that G of lambda star nu star is what? Minimize over all x such that fx plus summation fix lambda I plus summation hjx nu j. Right? Is it? And now I know that, so I know that this quantity is less than equal to f of x star plus, because this is minimum over all x, that's why it will hold for x star as well. So this inequality will hold for x star as well. Summation fi x star lambda star plus summation hjx nu j star, right? So, and now by dual feasibility, I know that this is equal to, so let me just keep it. So this is equal to fx star, right? This G lambda star nu star is equal to fx star, right? So what will happen? This fx star cancels, and this says that this quantity is positive. Okay. Now, since x star is a primal feasible solution, so this is 0. Okay. So what happens? This says that this quantity is positive. Now we know that lambda i's are all dual feasible. That is, all the lambda i's are positive, and I have primal feasibility. That is, fix star is less than equal to 0. So this is a sum of negative numbers, and I'm claiming that it is greater than equal to 0. Or this is sum of a non-positive numbers, and I'm claiming that it is greater than equal to 0. So that clearly implies that each one of them have to be 0. That is, for all I, fix star lambda I star is equal to 0. And this is precisely this complementary slackness condition. Okay. All right. So there were a couple of interesting problems that we could have done, but I don't think we have time. Let me just solve one more problem using KKT conditions. Okay. Yeah. So let me keep these conditions here as it is. And let's look at one problem that, like, it looks intimidating, but if you understand KKT conditions, that you can solve it reasonably easily. Okay. So the problem is, it's also called water filling problem. So it's, let's make sure that I don't make any mistake here. Sum overall I log of alpha I plus xi such that xi is positive for all I and 1 transpose x equal to 0. Okay, this is your problem. So alpha is are strictly positive and they are given to you. Okay, and you want to minimize over all x such that this holds. Okay. Okay, and so you can easily show that this function is a convex function. Okay, it's not very hard to show, and it is easy to see that you can find out one feasible solution. I mean, any like 1 0 0 0 0 is a feasible solution, right? So you have primal feasibility, you have convex set, convex constraints. So you can apply your weaker Slater conditions and you can say that strong duality will hold here. My KKT conditions are necessary as well as sufficient. They fully characterize my solution, right? So let's look at, so we don't have time, so let me just tell you what happens rather than going through all this. Or yeah, so now my primal, my primal and dual feasibility. Okay, so let me associate variable lambda I with each of this constraint and a variable nu with this constraint, this equality constraint, right? I require my lambda I to be positive, nu can take anything. So my primal and dual feasibility will imply the following set of conditions, right? That my xi star should be greater than equal to 0, 1 transpose x star is equal to 1, and lambda I star should be greater than equal to 0 for all I. Okay. Well, I'll write this constraint as minus xi less than equal to 0. Okay. This is clear? Now I have to write this, so I have to quickly form my Lagrangian. So my Lagrangian is minus summation I log of alpha I plus xi minus summation lambda I xi plus nu 1 transpose x minus 1, right? This is my Lagrangian, and I will take its derivative and set it to be 0. So that is equal to minus 1 by alpha I plus xi star. I'm taking derivative with respect to ith component, right? Minus lambda I plus nu, right? And I have to set this to be 0. Okay. So this will imply that my lambda I star, so this is all star, my lambda I star, or yeah, how should I write it? So this will just imply that my lambda I star is equal to nu star minus 1 by alpha I plus xi star, right? So let me just replace this, and this will give me my second set of condition, that is lambda I star is equal to nu star minus 1 by alpha I plus xi star. Okay. And then finally let's write the Slater, complementary slackness conditions. Okay, so complementary slackness condition just says that this should hold. So my Fix here is just minus xi, right? So my lambda I star xi star should be equal to 0. Okay. clear now? So now these lambdas are sort of auxiliary variables. I can get rid of them because I know that lambda I star is exactly equal to this. So these conditions can be reduced into these conditions, that xi star is greater than equal to 0, 1 transpose x star is equal to 1, then nu star is greater than equal to 1 by alpha I plus xi star for all I. Because lambda is greater than equal to 0, that means that nu star has to be greater than equal to this, right? So these are my conditions, and finally this time this is equal to 0. So nu star times x star is equal to x star by alpha I plus xi star. Sorry, right? Just simple this. Or I should not write it like this, it will be some sense incorrect. So times xi star is equal to 0. Okay. So my KKT conditions reduces to just these simple conditions. Right? And now note one thing, which is, first consider a case where if my nu star is greater than equal to 1 by alpha I. This is the case we need to consider it. Or actually easier case will be. So there can be two cases, right? One is nu star is less than 1 by alpha I, and second is nu star is greater than equal to 1 by alpha I, right? So if nu star is less than 1 by alpha I, then what happens? So if this is less than 1 by alpha I, then I cannot have xi star. So my xi star has to be positive, right? Yeah. Okay. It has to be greater than 0. If this is greater than equal to 0, then this will say that my nu star has to be equal to 1 by alpha I plus xi star. Right? Is it clear? If nu star is less than 1 by alpha I, right, this quantity I'm saying is less than 1 by alpha I. So that can happen only when xi star is positive. Otherwise, it cannot happen. Like this is strict inequality. This is strict less than equal to, less than, sorry. So xi star has to be positive. So this will imply, and if xi star is positive, then this quantity has to be 0. So this will imply that nu star is equal to 1 by alpha I plus xi star, right? That is xi star is equal to 1 by nu star minus alpha I in the first case. In the second case, I know that nu star is greater than equal to 1 by alpha I. So if I have xi star to be greater than 0, that cannot happen, right? So xi star has to be equal to 0, and my v star has to be, sorry, nu star has to be equal to, sorry, has to be greater than equal to, or can be greater than equal to 1 by alpha I plus xi star. That's all I have here, right? But wait, what am I saying? So in this case, my xi star, I don't care what. In this case, my xi star has to be equal to 0. Okay. So by looking at these two cases, what does it say? That my xi star is equal to maximum of 0, 1 by nu star minus alpha I. That's it. So if it is, so either it is 0 or it is equal to this. This is always a positive quantity. Okay. by primal feasibility, this always has to be greater than or equal to 0. So if it is greater than or equal to 0, either it has to be this or this, right? And now the problem is solved in some sense. I have solution for my xi star, and it is in terms of just one dual variable v nu star. Okay, so how can we determine this dual variable? So we haven't used this condition so far, so that's all we will use. So this condition says that summation xi star is equal to 1, which implies that summation max of 0 comma 1 by nu star minus alpha I is equal to 1. Okay, so this is a increasing function in 1 by nu star, and I have to just satisfy that 1 by nu star, I have to set 1 by nu star so that this is equal to 1. So this can be done easily. I mean, keep on increasing 1 by nu star slowly so that you hit 1, or you can do binary search or bisection method type of. Okay, so this is easy to satisfy. And once you have 1 by nu star, then your xi star is immediate. You immediately get it. Yeah. So all the problem here looked very complicated, but if you look at the KKT condition, analyze it properly, you can still solve it almost, in closed form. Okay. So yeah, I mean, the main points would be that whether you have a convex problem or not, you can always form concave dual problem, which is reasonably easy to solve. But in addition, like if your Slater conditions are satisfied, then you have strong duality. That's why solving dual is equal to primal. And in that case, you can consider your KKT condition, which consists of 3 things: primal and dual feasibility, which is natural; stationarity of your Lagrangian, that is your Lagrangian gradient of your Lagrangian should be equal to 0 at x, and the complementary slackness condition. So these 3 things will be necessary and sufficient if strong duality holds. All right. Okay. So we are out of time. Any questions? Any doubts? All right. So I guess Vishy will teach you next class. He'll talk about support vector machine. So there you will see how these KKT conditions are used to solve support vector machine. He'll provide one algorithm for that. Okay. All right.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.